Guys, so I finally got, do what? Anything it says for homework, yeah. Okay, so I finally got my rig set up. So from here on out, if you are not here, I'm going to still try to post the videos. I typically do not have a virtual Algebra 2 class anymore. Everybody either came back or is in regular Algebra 2. So I don't have one. If you are quarantined, obviously you're not going to be here for a week or so. So I'm going to need to have the videos up. But I don't have anybody quarantined. But I'm going to still try to put them out every day. So if you want to review, sadly, if you fall asleep in class, if you're sick, whatever you'll have. But I'm going to be recording my meets. So what that means is I'm going to run a meet live all day long. So you guys, if you're at home, just hop on during fourth period and just join the meet. It's the same hurry _ meet _ 2020. And should you forget that, if you can text me before I start teaching during the day, I'll probably see it on my phone. I can text you that back. But if you want to write that down somewhere on your notebook, so if you're not here, just join the meet fourth. You could also join fifth, because I probably will just run it all day long. And fifth period, we have lunch and study. I don't know how much you want to just hear my fifth period, although they are pretty entertaining. Especially Martina in the back, who's just a nonstop flow of random, bizarre questions to the class. But anyway, in that class, it starts at 12:30 to 1:20. But I'm going to try to record those. The only downside is this. My phone, when I record and I upload it, takes roughly 30, 40 minutes without, unless there's a bad glitch. Sometimes there are glitches, but it's pretty consistent. Within the hour, I got it uploaded. With Google, recording the meets, I've gotten them as quickly as 10 minutes, and I've gotten them the next day. So it processes them and sends me an email link. And I have no control over that. If Google's having issues, which they do from time to time, it's down. Y'all with me? So anyway, like this one right now is getting recorded for whomever might not be here. Who's not here?
Oh, it's weird.
Weird. That's right. Okay. So he's probably not logged on, but in the future, he could just log on, or if you're watching this at home, you can log on during this period and then just watch it. And if you yell real loudly, I can probably hear you from because I have to do it from this computer over here so that I still have access to my other video. It doesn't know how to, I haven't been able to figure out how to let it use both. It wigs out and just shuts down the meet when I try to use this camera and that camera. So in the meantime, I'm using this one. So if you are at a meet, you can yell at me and I'm like, hey, what's your question? And I could probably answer your question as well too, which kind of keeps you in mind. All right? We good?
Yeah.
All right, how you feeling about ellipses and hyperbolas?
Pretty cool. Easy.
Okay, yeah, everybody says easy after the first day.
Oh, great.
And on the second day, and they're like, oh wow, I take that back. I just realized I wanted to show you something, and I can't. Do I have a piece of string?
That's a great question.
Dang it. In my other classroom, I keep it hanging, just dangling from the side of the board, if you've ever noticed it. Well, dang it. I wanted to create an ellipse from the definition of an ellipse. So I can't really show you, which is sad. I'll try to remember and go and get some string and show you on Monday maybe why the definition makes what it is. Okay, so all right, let's just start over here. We're going to talk about part 2, ellipses and hyperbolas. Now, remember how there's a definition to a parabola? Yeah. And the real definition is all the points in a plane, they're the same distance from what? A point called the focus and a line called the directrix. Awesome. And there's a definition for circles, which is actually, I could use string for that too, right? Put a fixed point there and a fixed length and just sketch it out like this, right? That's the whole idea of a compass, what a compass is doing to create a circle. Homer has like a built-in compass on his hinge on his elbow that makes him perfect, but that's the idea of a compass. of a compass when it acts? Well, an ellipse also has something, a definition like that. It's a little uglier, but I'm going to put it up here. An ellipse's definition is all points in a plane. How do I word this? A good way to word this. That have a sum of focal distances from 2 points called foci, focus 1, focus 2, which is constant.
Are the foci the vertexes or?
No, the foci are kind of like the centers. They're inside. You'll see it in a second. But again, you're going to see it pretty roughly because I don't have an actual piece of string, which is unfortunate. Normally I can kind of think of a way to do this.
Shoelace.
I could, although I don't really want to take off my shoelace. Although that's good. I'll keep thinking. I have actually, all right, we're going to make this work. It's not going to be great. It's going to be something new. All right, so this says all points in a plane that have a sum of focal distances, or what the real name is sum of focal radii, from 2 points, which is constant. So the sum of focal distances, or the sum of focal radii, is constant. What that means is, do you know how the length of the radius was constant and never changed? Well, instead of coming from 1 point and having 1 radius, imagine if you had 2 points and there was a length, basically a length from 1 point to the curve to the other point. And that length was constant, but the individual lengths changed. So like one time, one length could be 1 and the other one 3. One time the length could be 2 and the other one 2. Are you following me? But the sum of the 2 lengths is always constant. So this is not going to be that great, but pretend that this iPhone cord, this is going to be awful actually, but something. Pretend that this, anybody want to give me their shoes? Nobody?
I'll do it.
You take one for the team?
Take one for the team.
Actually, it'd be really great with a shoeless. Would make it look like a point.
Here you go.
You're the man. Right. So here's my first focus. And that's weird. Again, I have it stuck on the board so I don't have to remember. Keep a running list. Every day I go down and grab something else from that room that I forgot.
Is there someone in there teaching?
Mm-mm. There was supposed to be. Miss Leon, Chef Leon was supposed to be in there, but okay. This is going to be a big one. All right. All right, so this will help you visualize the definition too. That's really slimy. Okay, so pretend, not the lace, but the board. The board is slimy. So it's not sticking. No, your laces are, perfect. Okay, so pretend that this is a focus, right? Remember, you only had one focus on a parabola, right? Pretend that this is a focus. Yeah. Pretend that that's a focus. Plural of focus is foci or foci, depending on who you talk to. And yes, there is a center in between there that we marked up yesterday. You saw that, but it's really not important in the definition. This represents the sum of focal radii or sum of focal distances from the 2 points. And that length of the string is not changing, is it? Right? So whether the point exists here, oh man, I missed it. Whether the point is there, or whether the point is there, or whether the point is there, or there, or there, or anywhere on this, are you tracking with me? These points make up your ellipse. I'm trying not to turn your lace pink.
It's all good. These are my gray shoes.
Are y'all with me? So the sum of focal radii is constant. And those are your focus, which are your foci, which I didn't even mention yesterday, did I? Nothing. What did I mention yesterday? When it comes to sketching, and this is a stretched one this way, so you would have had something like this, right? And you would have had some number squared there. Well, I'm going to give it a name today. Right in the middle of this is your center. Okay? Nobody's going to say it? What are you thinking right now? Literally 28 years, somebody said smiley face every single time. I can't let it stop right now. Yeah, everybody's always thinking, oh, it's a smiley face. Okay, so right here, there's the center. We talked about that. And we said that the length from the center to what?
Vertex.
We didn't even mention the focus yesterday. We said the vertex, which is way out here, or way out here, we said that length was what? The number that went below the x if it stretched this way, or y if it stretched the other way, right? But always the center to the vertex for us is A. So had my graph done this, and had that been the vertex, and that been the vertex, your foci would have been in here. But still, from there to there is what? A. So we're always going to put A is always going to end up being the bigger of the two numbers. Are y'all with me on that? Mm-hmm. So whatever the big distance is A. That is not true with hyperbolas at all. On hyperbolas, A is always going to be the first one, whatever came first in the problem here. But on a ellipse, that's not the case. Always the biggest. So it's in your notes. If you're looking at your notes, A is always bigger than B with ellipses.
But why does it matter if we're going to actually fill in like real numbers?
You'll see why in a second. But good question. So right here, I'm going to mark this little dotted line. And that right there represents my A value. And A is definitely in this equation, right? And you saw that yesterday. If you just count that distance, it's A, square it under the X. Or if it's going this way, square it under the Y. All right? Now, this length right here is B. And that point at the end of that doesn't really have a name that I know of. And you already know that you square whatever that length is, right? But now you know that the smaller of the two values goes here. Well, that's the distance to the vertex. The distance to the focus also has a name. We call it little c. Not big C for center, but little c. Okay? Now, there's a relationship between A and B and C, and right now it's kind of hard to see it. I know that C is smaller than the A on an ellipse, but here's how I'm going to help you see it. Right here, if the distance from the center all the way out to the vertex is A. That's got to be true both ways, right? So that means this would also be A. Right? Now, think about the length of this string. It may not seem like it, but the length of this string is always the same length as the ellipse. Now, it looks like right now you're like, no way, it's longer because look, you got so much hang right here. But let me show you and prove it to you. If I bring this across to right here, I'm landing on that point, right? You see it now? I could cut that section and put it over here, and the length of the string, which is the sum of focal radii, is the same length as the ellipse, right? And didn't we have a name for the big length on the ellipse?
The major axis.
It's the major axis. So on an ellipse, the major axis always has a length of what? 2a. And if the length of the major axis is 2a, then the length of the string is also 2a, right? Which means, right?
Yeah.
Which means the sum of focal radii
It's 2A.
is also 2a. All right? And then here's where I can put something together for you. So what would happen if I took this and brought it straight up to the top? I'd be right there. What would be the length of each half? That would be an A and that would be an A. And wouldn't that make a right triangle? Except this right here is not that. What is this?
C squared.
C. So there is a Pythagorean relationship between the A and the B and the C value on an ellipse, but it's not C squared equals A squared plus B squared. Although ironically, that is true on a hyperbola. But on this one, what is it?
B squared plus C squared equals A squared.
So the A squared equals the B squared plus the C squared. Are y'all seeing that? So here's what they do a lot of times. They'll give you this and they'll say, hey, how far away is the focus from the center? And you don't see that here, but you'll go, oh, wait, the focus to the center is C. So I can take my A and my B value, or even the A squared and the B squared value, plug them in there and solve for C, and that's the distance from the focus. What's more likely, though, is they give you something like the focus, and maybe they give you both of the foci, or foci, and you go, oh, if they gave me two of them, then half that distance is C, right? Right?
Yeah.
And then if I gave you maybe the sum of focal radii was 12, you go, oh, A is 6 then. So now that I know A and I know C, I can plug the A and the C in there and solve for B. And the whole goal usually is to either graph an ellipse or to find what the equation of the ellipse is. And either way, you got to know A and B. So what they like to do is give you, they or me, whomever, the book, me, math tournaments, they want to give you just enough information, not too much, but just enough to enable you to put it all together. But that's the link that links the graphing part, the actual graph, and all the parts of the graph to the actual equation. And you'll notice you didn't have to know any of this to take an equation and graph it, did you? You didn't have to know what A was, you didn't have to know what B was, you didn't have to know what C was. You just have to know certain properties. So hopefully now that I'm throwing all that extra stuff on there, you can piece these two together. But there's a lot going on, just even right now. But remember, the sum of focal radii is the same as the length of the string in our example, and also the length of the major axis. And while we're at it, what's the length of the minor axis? 2b. So you should be able to look at stuff, just look at an equation right there and go, oh, if the big value is A, find the A, double it, and you know all of those. Find the B, double it, and you know that. You seeing it so far? Okay, now, do you remember what that line was called on a parabola that went through the focus? No, on a parabola that went through the focus.
Oh,
So on a parabola.
The axis of symmetry. Yeah.
Well, that's actually true. I want it the other way. If that's your focus, say this is your focus right here. What was that segment called? That's the latus rectum, right? That special one that went through the focus. And this is not the scale, but you remember that? Well, this actually has two of them. Two, the plural of latus rectum is latera recta. Latera recta. Okay? But like the parabola, it's the width of this going through the focus. So it still is this length right here. The only problem is it's not 1 over A anymore. I mean, clearly, say A was 10. Is this 1/10? No. So I can't find it by doing 1 over A. Now, this used to be the hardest problem on my test. I would say, find the length of the latera recta. And people are like, ugh. And this is what you would have to do. You would have to first find the focus. Okay? Say the focus was at, say that point was at like 2, -4. Which means you had gone over 2. Right? And then down 4. And then you'd have to plug in that 2 into the actual function for x and solve for y, which is kind of a pain, right? A lot of algebra there. And because y is squared there, you'd have to square root it, and you'd get 2 answers. You'd get this value for y, and then you get this value for y. And then to find the distance or the length of that latera recta, because again, there are 2 of them, one there to the focus, one there. You could take those 2 values and subtract them and find the length between them. And that's what we used to do. And then one day I went, man, there's got to be a better way to do this. Now, granted, the internet's come out now. So now you could go length of the latera recta and it spits out a formula. But back in 1995, you couldn't do that. Or if you did, it would take 45 minutes for the internet to give you a response because it was like dial-up internet, and it's super slow. It once took I remember the day when they came across the intercom during like a professional development day, and I was working in my room, and they were like, if anybody would like to play with the internet, please come to room so-and-so. And I'm like, cool, internet. So I walked on down there, and like 3 of us showed up, like literally the entire faculty. People were like, that's just a fad, right? So I went down there with Mr. Health, not the one that works here, but his dad used to work here. I went down there with him, and I was going to go skiing, or I had plans to go skiing up in British Columbia, a place called Blackcomb, Whistler. And I was going to go up there, and ended up not going for whatever reason. But I remember going, I'm going to download their trail map. So I got on the internet, found their website, took only about 15 minutes. And then I found it, and I clicked on the download. And I mean, it was like, I sat there for 10 minutes, and I think I got 2 lines of screen to come down, like pixel lines. And it was not like high def back then. So I went to lunch, gone about an hour and 15 minutes, came back, and now I was at like half the screen. I mean, it was so slow and pathetic. It was awful. And why am I telling you this?
Great question. I don't know. You're talking about how
You
you
can't
look up
have
the internet.
Yeah.
Oh, yeah. Well, things are easier to access now, but a lot easier than they were before. But that's what I used to do. I used to just crunch numbers to try to come up with better formulas to make it easier at math tournaments. So I did that. I took this, and I left the A and the B in there, because I figured it probably doesn't matter where the center is, but the A and the B control the size of it, right? So I put a random center, but left the A and the B, and I plugged the value of the focus in there and solved, and guess what I kept getting for the, and then I took them and I subtracted the 2 Y values, and when I did that, I came up with the same formula, whether it was stretched horizontally or vertically, and that formula was 2b squared over A. And the children rejoiced, because now they didn't have to do any of this anymore, right? Now when I say what's the length of the latera recta, all you have to do is make sure you pick the right one for A and the right one for B, right? But which one's A?
The long one.
The big one. So as long as you pick the correct A, not the A squared, but the correct A, and the correct B, technically I guess B squared, but take those and plug them in, it gives you the length of each of them, not the total. So it gives you the length of each of the latera recta. So if you get a length of 10, that means this one's 10, and also that one's 10. I'll never say what's the sum of the lengths of the 2. Are you with me? So with this in mind right now, we should be able to find every possible thing associated with this. Now there's one more thing. Anytime you're going to have a focus, you're also going to have a directrix. And these do have directrices, and they are located actually on the other side of the vertex somewhere, but they're not positioned in the same way they were before. But there is a directrix here, and there's also a directrix somewhere over here. I have yet to decide whether I'm going to test you on that this year. I know I do next year. I may or may not. If I do, I'll let you know. But there's a formula for it in there. And basically what you do is you start right here with this. And first thing you got to do is decide, well, if my parabola is stretched this way, then what kind of lines do I have right here? I'm sorry, my ellipse is stretched this way. What kind of lines? Horizontal or vertical? Vertical. And verticals are always x equal, right? So what you do is you go, all right, if I wanted to find those, I go x equal, and then I choose the h value, because I'm going to begin here with h, and I am going to add and subtract that distance that occurs there. But that distance that occurs there, first we got to talk about eccentricity and something else. And I actually have not done the research as to why this works the way it is, because the only people who ask this question are like Vestavia. They're just dirty. Like I didn't even know it existed until they asked it one year. But you got to add or subtract this, I believe it's C over A or E over A. I forget it every year or two. But it's there's a value that you're going to add that has to do with eccentricity that you add to get to that or subtract to get to that. And if the thing was stretched this way, like this, then your directrices would be like this. Are you with me? Which means they're horizontal, which are always y equals, and you're going to be starting with the k value and add or subtracting that exact same value. And the formulas are in your notes. So the two formulas are in your notes, and those give you the equations of those two lines. But I have a sneaky suspicion I'm not going to ask that this year unless it's a bonus. But I'll let you know Monday at the latest. Are y'all with me? Okay. Trying to think of anything else I've missed. We talked about area of one of these.
Yep.
It's always what? Not pi RR, but pi
AB.
AB. Right? And try to put the, don't put like pi 12. I mean, the formula is pi AB because it is. But when you write your answer, write it as like 12 pi or 36 pi or something like that. All right? Let me double check on this and see if I'm forgetting anything before I go to hyperbolas. Okay, eccentricity. Now, we've already said that eccentricity was 0 if it was a circle. And we said eccentricity was 1 if it's a parabola, okay? And it's always that, so there's no real formula on how to calculate it. It's always 0 or 1. Well, ellipses are in between there. So your eccentricity is always going to be bigger than the 0, smaller than the 1. And the closer it is to 0, the more circle-like it is. The further away it is from 0, the more stretched out it is. So if you get an eccentricity of, but it's not like you would think. You'd think, oh, eccentricity of 0.6, that's way away from 0. It still looks pretty circular, and you'll see that. But if you start getting an eccentricity of 0.9 or 0.95, really thin. And if you start getting one of 0.9999999, it's super thin. It almost starts to look like a line. It's so skinny. Okay? But there's a formula for it. And the formula to find that actual value is C over A. And the great part about latera recta and eccentricity are it's the same value whether you're dealing with an ellipse or whether you're dealing with a hyperbola. So you don't have to remember a different one, except on a hyperbola, when you do C over A, you end up getting a different number. On a hyperbola, go ahead and mention it. Hyperbola, you still are going to do C over A, but your eccentricity is greater than 1. But the great thing is for your test, you can just remember, eccentricity is always C over A for hyperbolas and ellipses, 1 for parabolas, 0 for circles. And latera recta, always 2b squared over A, but don't confuse that with latus rectum. Latus rectum goes with a parabola, and a latus rectum, if it goes with a parabola, that's 1 over A, right? Or flip the A value. And is there a lattice rectum with a circle?
Yes, it's like the middle. No.
The closest thing to it would be a diameter. Because what do you think happens to make this circular? What do you think the foci end up doing? You end up doing what? If you pull them in close enough, they land on each other at the center, and then your string just makes one big circle. And if the foci end up being the center, then the distance through the foci, which is really the center, would be the diameter. But we don't even say that we have a ladder rectum in that case. Although it would make sense, because if you think about it, if B and A become the same thing, they cancel, and you get like 2B or 2A, which is like 2 radius, 2R, and 2R is the diameter. So it kind of is the same thing, but we just think diameter. We don't need to mess up circle information. We already got that there. Y'all with me? And then looking at this other stuff, some focal length, I think that's everything. Yeah. So that's everything you need to know about an ellipse. Believe me, I know that's a lot, and it's going to feel like even more once I slam you over the head with hyperbolas. Okay? So let's shift gears and jump to hyperbola. Now, sadly, I can't do a fun little string example with hyperbolas, although I greatly appreciate
Thank you.
the string. Do that again. Save the day. The reason why I can't do the string example with a hyperbola is it's not going to be a sum of focal radii. It's going to be a difference of focal radii is constant. What that means is like 6 minus 2 would be 4. 10 minus 6 would be 4. 100 minus 96 is 4. Well, those numbers start getting huge, don't they? There's no limit to what they can be. So the distances, these points can get way out of hand. Whereas the points on an ellipse are right here, the points on a hyperbola go out infinitely. So the definition, I'm going to erase all this. The definition of a hyperbola is similar to this. Okay, the definition is similar, except for a hyperbola, it's all points in a plane that have a difference of focal radii distances, or focal distances from 2 points, which is constant. That's the only difference. But it's much harder to show you a diagram. But if I do draw a really good one, which I will attempt to, I can pick some random points and do some measurements, and I bet my measurements will be close. And you'll be at least moderately or mildly convinced that I'm not lying to you. Okay? So let's describe this. This is essentially what it's saying. So we already talked about, let's just say I had a center right here. I'm going to try to do this as to scale as possible. So 1, 2, 3, 4, 1, 2, 3, 4. Let's go with 1, 2, 3. That look kind of accurate. No. Better off I am here, the better off I'm going to be. So let's just say I had this. X, I'd gone 4 that way from some center. I went 3 up and down from some center. Right? I took this, I sketched a box. Semi-accurately. And because X, because X comes first, what do? So I'm from here, and this is where it gets off, is I really am just guesstimating what these points would be. And then I didn't have to guesstimate at all because the string dictated the points. Okay, so let me describe what this definition is basically saying. All right, here we go. All points in a plane, and you can see them with the brown lines. Those are the points in the plane that were on this hyperbola. I am going to pick a couple. Like if I picked this one. According to this, the difference in focal radii. Now, the focal radii before was focus to graph, graph to focus. Those were the two focal radii, and the sum of them was constant. What they're saying now is the difference of them is constant. So right here, focus, this is not a focus, this is a vertex. But let me show you where the foci would be. You don't know this yet, but I'll confirm this in a second. So here, the relationship between A, B, and C is not A squared equals B squared plus C squared. It's C squared equals A squared plus B squared. And I'll show you a clever way of remembering that in a second too. So if I know that A comes first, it's not A because it's biggest, it's A because it's first. So the A is first with hyperbolas. B is the second one. So I'm going to take A squared, B squared, solve for C, and I get 5. So this is where my foci would be. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. All right, so according to my rule, the difference of the focal radii would have to be constant. So let's just say I picked that point. So my difference would be whatever that length is. Try to make it accurate. Minus whatever that length. Okay? So if I subtracted those two lengths, that should be the same if I do this for any other point. And I should get the same thing every time. So I'm going to pick another different point, like maybe this one. And that means that this length right here and this length right here should also, if I subtract them, give me the same thing. Now I know that this ruler and this graph do not have the same scale. Okay, they don't. But I think the difference is you can still see it. So right here, on my ruler, this is like 20.5 minus 7, so 13.5-ish. And this is 17 minus 3.5. Oh, no way. 17 minus 3.5? 13.5-ish. So the difference in the two focal radii will always be constant. So that's what controls the points here, except I really can't use a string because the sum of focal radii and the difference of focal radii, although the same, the string is always one length, but the individual lengths here can get infinite.
Are we going to do this on the test?
I'm sorry?
Are we going to do it on the test? Are we going to find it?
No. I'm not going to make you verify any of that kind of stuff. But I am going to tell you this, that the sum of the focal radii, do you remember the sum of the focal radii was 2a on an ellipse? It's also 2a here. Because look, 13.5, a was that distance to the vertex, right? Isn't that how you sketched the box yesterday or last night? Didn't you go over here and take the A and you moved left A and right A, didn't you? Because it was beneath the X. Are you with me? So you went that amount there and there. So if the difference of focal radii, if the difference of focal radii is 2a, then this little length right here should measure 13.5. Can you see it? 13, 14, 13.5. So the individual differences is the same as that. Now I know if you're frowning right now and going, but that's 10. I know because this scale doesn't match that scale. If I had a ruler that was exactly like that, or maybe I should have done that. But the point is that this right here, this length right here is the same as the difference between those two lengths. This length right here is the same as the difference between those two lengths. On my ruler, it's 13.5. On this grid, it's 10. Okay? So ignore the 13.5 thing. I was just trying to measure to confirm to you. But my point is, right here, at 2a, this distance, I'm going to get rid of these little crazy lines right here. And that one right here. Yesterday, you took that distance and marked it left and right. Or not 10, 8, sorry. You marked it left and right. You said 4 that way, 4 that way, last night on your homework. That is your A value from the center. Then you took this value, which is 3 squared, and you went 3 up and 3 down. That is your B value. Your A value always is the distance to the vertex, whether you're going this way or whether you're going this way. So what is the length? If that's the vertex and that's the vertex, what is your length of your transverse axis?
2A.
Always 2A. And remember, A isn't the biggest on this. A is the first. You see, that's the A squared. And if that's 2A is the transverse, what's the length of your conjugate? 2B? And what's the distance to your vertex? Vertex.
Oh, C squared.
Vertex.
From 2A.
From there, the distance from your, I'm sorry, I wasn't clear. From your center to your vertex is A. What do you think the distance is from the center to the focus? C.
Oh.
Now, I don't have, again, there's no Pythagorean fun little example I can show you there to prove to you that that and that is the same, but it is. I just can't because there's no string example. But right here, that distance there is the same as that distance there, and A squared, B squared, C squared are related that way. Now, people get that confused on how I remember. So how I remember it's on a hyperbola that it's C squared equals. How do I remember on an ellipse that it's A squared equals? Let me show you a little way to, it's kind of dorky, but it helps most people. So let me give you 2, and let me just show you. So let's just say I had an ellipse that looked like that, and I had a hyperbola that looked like this. So do this, okay? If there's you don't even think about a C squared right now. If that's, what is this right here?
4 squared.
This is an ellipse. So would that be the A squared or the B squared?
A, that's the A.
It's an ellipse. A squared is always bigger. Which is the A squared here?
16.
16. Why?
Because
A squared is always first. So what I see here is an A squared there and a B squared there. Well, if you look at that, take the A squared, change the sign, put the B squared, set it equal to C squared. Right here, take the A squared, change the sign, take the B squared, set it equal to C squared. And you don't have to think so much. So if it's an ellipse where there's a plus, go A squared minus B squared. If it's a hyperbola where there's a negative, go A squared plus B squared. Set them both to C squared, and then it's just a pattern that you do every time. And if you think about it, doesn't this end up giving me the A squared equals B squared plus C squared that we said in the example? And this already says C squared equals A squared plus B squared, which we said in the example. So if you like that way to remember them, most people do moving forward, they go, oh yeah, for these, just take the A and the B and subtract them. From here, take the A and the B and add them. And you've got to be subtracting from big minus small because A squared is always the biggest here, so you never get negative under the wrap. So difference of focal radii, same. There is no sum of focal radii. There is no major and minor, but there is transverse and conjugate. There also is a length of the lateral recta, but what is that?
2B squared.
2B squared over A, same thing. There's no area that you have to deal with. There is a...
Isn't it lattice structure for hyperbola?
Hyperbolas? Each one is called a latus rectum, but plural is lateral rectum. So I think in my notes I said the length of each latus rectum. So these have lateral recta in them. Look, there's the focus. The width of the graph at the focus. That width, 2b squared over a. Right here, here's the focus. The width of the graph at the focus. That length right there, 2b squared over a. So if you were sketching this and you really wanted to have a couple extra points, other than just that point and following the asymptotes, you could mark the focus, figure that out. Say you figured that out and you found out it was 8. Go up 4, down 4, you get 2 extra points, and then you sketch it. I don't do that. It's, to me, a waste of time. Yes, you might be this much more accurate, but it's almost negligible. Making sure I don't forget anything. Eccentricity, we already mentioned that. Same thing, still C over A. So once you find your C value, take your C value, and look at, there's your A value's 4. Look at that. If A is 4 and C is 5, what happens when you do C over A? 5 over 4, it's bigger than 1, sure enough. So if I were to walk up and say, hey, the eccentricity is 0.7, what do you immediately know about the graph? It's an ellipse. The eccentricity is 1, what do you know? Parabola. The eccentricity is 0, you know it's a circle. Eccentricity is 1.3, you know it's a hyperbola. And you know that because of that. But if you need to calculate it, for those two, it's C over A. There's no calculating the others. Okay, making sure we did not get to do many examples. We may or may not do that game. I really want to do the game, but I also want to make sure you're in a good place for your test more than I want to do the game. And by the way, these also have directrices. Where do you think the directrices would be? I'm not going to ask you that. Or just where do you think, unless it's a bonus. If the focus is here and the vertex is here, where do you think the directions are?
Like on A.
Actually, they're somewhere in the middle somewhere. But you would find them the exact same way as I mentioned before. All right, guys, I think I covered almost everything. I know I've hit you over the head with it. It's a lot. Do the best you can on the homework. And I really might shift gears on Monday. I might use Monday to oh, no, wait. No, we are good. We're reviewing. So I'll use Monday to do a bunch of examples, and we can still, you'll be reviewing, and then you'll have Tuesday to review because you guys won't even be in here, and then we'll still play the conics game on Wednesday. Yeah, we're in good shape. Do the best you can on your homework, and don't lose heart, though, because it can be a little tricky.
And is the homework for tonight the only one, or the homework from yesterday the only thing we turn in this week?
Yes. All right.
I turned in everything.